Okay, good evening. This is Professor David Okay. My topic for tonight will be a long video format discussion, and this is on the topic college algebra. And I am now on lesson number 74. Okay, lesson number 74. Okay, let's proceed. We are running smooth on college algebra. So for those of you who are following my channel on the subject matter long video format discussion college algebra, we are now on lesson number 74. Okay, the title of the discussion for tonight will be college algebra lesson number 74, and the title of the topic is applications of linear equations, okay, underscore distance problems. The last time around, I discussed application of linear equations involving number problems. Okay, number problems and distance problems are actually favorite subject matters on the SAT and CAT exams. Even in the board exams, they are giving distance and what you call this number problems. Okay, let's proceed. I will try to give you two example problems for the what you call this distance problems. Distance is actually there's only one formula needed in the so-called distance problems. That distance is equal to the product of rate times time. That rate should be the so-called a constant speed or rate. It's not accelerating. That is distance is equal to rate times time. This is the only equation needed in the what they call the solution of distance problems under linear equations involving linear equations. It will just be simply distance is equal to rate times time. Rate or velocity. Time is the time involved, but this rate here should be constant. It's not accelerating. Okay? Okay, I will try to fix this one so it will look good. So we now know the formula needed in the so-called distance problems. Okay, I will give you example number one. Sample number one and number two here are actually almost similar, except in the so-called formulation of the algebraic equation to solve the unknown. Okay, I will try to read the problem. Two cars left a gasoline station at the same time and headed in the opposite directions. How far from each other will the cars be after 2.5 hours if their speeds are 124 kilometers per hour and 110 kilometers per hour respectively? The problem is just easy if you try to figure out first, okay? So we will be drawing a horizontal ground here, okay? And at the middle, we put a vertical line, and we put here, this should be the gasoline station line. It's the reference point where the first car and second car actually move from each other, right? This should be the first car going to the right. This should be the second one going to the left. Okay, the speed of the first one is 124 kilometers per hour. The speed of the second one is 110 kilometers per hour. So this is slower than this one. This is faster. Okay, the problem is just asking how far from each other. The distance between the two cars, okay, after 2.5 hours. After 2.5 hours. This started here on the gasoline station. This one goes to the right. This one goes to the left. This speed is 124. This speed is 110. Right? And the problem is just asking how far are they after 2.5 hours. Oh, that's an easy problem, right? We figure out it already, right? The distance traveled by car number 1 with respect to the gasoline station is D1. And the distance traveled by car number 2, that is the one going to there, is distance 2. And the total distance separating the two cars, okay, after T hours, T is equal to 2.5 hours. So the problem is asking how far are the two cars after 2.5 hours? It's an easy one, right? Because actually from the figure alone, we could figure out the, what you call this, the formulation or the algebraic equation. That is the distance D should be equal to the sum of D1 traveled by the car going to the right, plus the distance traveled by the second car going to the left. So our equation here is small letter d without any subscript should be equal to D1 plus D2. And that's it. Right? So if we now try to bring out the translation of the equation, we translate the verbal thing to a certain equation, right? That is total distance d. Okay. So for this one, I will just put a small letter d here. Letter D, small letter d. Right? The total distance is small letter d without any subscript. It will be equal to d1 plus d2. Right? From the figure. So the problem is just asking better yet, we'll replace this one with capital letter D. And we replace this one with capital letter D. So it commensurates with the equation on the figure, right? This is big D. So from the figure, the total distance separating the two cars will be represented by capital letter D. I replace it. It should be D1 plus D2. Should be the distance traveled by car number 1 plus the distance traveled by car number 2. And by using the equation, what's happening? Distance is equal to rate times time. The one I told you a while ago. That is, the distance traveled by any one moving in straight line will be the rate times time. So the problem is just asking what will be capital letter D after 2.5 hours. So actually there is an unknown here. No unknown, because we are given the time, right? So this is just a direct substitution one. We just plug in the values of speeds and time to the equations, and we can solve the problem already. Because if we try to designate this one here, distance 1 will be rate number 1 times time plus rate number 2 times time. Oh, that is just the formula that we needed, right? Distance is equal to rate times time. So meaning to say, distance 1 will be rate number 1 times time. Distance 2 will be rate number 2 times time. So by using this equation here and substituting values, R1 is 110 kilometers per hour. The time is 2.5. The speed of the second car is 124. Again, the distance traveled by it after 2.5 hours will be 2.5. So it will be 275 plus 310, and the total answer here is, I forgot to put this in the box. It will be 585 kilometers. So meaning to say, after 2.5 hours, the distance between them is actually 585 kilometers. Okay, and the distance traveled by the first one is 275, and the distance traveled by the what do you call this, speedier, okay, the faster car is 310. So the distance between them will be the sun, and that will be 585 kilometers. As simple as that one. Okay? Okay, let's proceed with example number 2. For example number 2, it's almost the same, but the verbal thing is different, right? The verbal explanation. A bus and a car start at a given point and travel in the same direction at an average speed of 120 kilometers per hour and 145 kilometers per hour respectively. After how many hours will the two vehicles be 15 kilometers apart? Oh, a little bit catchy than the first one, because the problem is asking after how many hours will the two vehicles be 15 kilometers apart. Okay. Of course, the first one is faster, 145. So even though they start at the same time, okay, the speed of the first one is 145. So gradually, this will, what do you call this, it will cover up more distance than the slower one. So later on, there will be a difference in the distances traveled after how many hours, right? And the problem is asking what will be the time when the distance between them is actually 15 kilometers. Because whether we like it or not, the faster one will go ahead, right? And the slower one will lag behind. And the difference in their distances traveled, there will be a difference. And the problem gave us 15 kilometers. And the problem is asking what will be the time that will elapse before their distance apart is actually 15 kilometers. Okay, let's try to bring out the figure. We draw a horizontal ground. This should be the bus. This should be the car. The speed of the car is 145 kilometers per hour. Obviously, cars are actually faster than buses. It depends. Oh, because buses actually got, what do you call this, many passengers, right? Many passengers. I'm fixing the wheel of my board. Okay? This is 145. The bus is 120. And they are traveling in the same direction. Okay? So as time passes by, this will go ahead. Okay? And the problem is asking, when their distance between them is 15 kilometers per hour, 15 kilometers, what will be time t equal to? Okay? That's the unknown. So if we try to bring out the representation, we place distance here is equal to rate times time. D1, as long as we are solving distance problems, this will not change, right? For the D1 is the distance traveled by the bus. I place it as simply 120 times time by using this equation here, right? Because the unknown time is actually t, right? And for distance 2, the distance traveled by the car, it is faster, right? So it will still be, it will be equal to 145 times the unknown time, right? So this is D2, this is D1, and as time passes by, whether we like it or not, there will be a difference in the distance between them, and the given problem give us 15 kilometers. So if we now try to formulate or translate the given representation to an equation, it will be this. Okay, that's the equation. Meaning, the distance traveled by the car minus the distance traveled by the bus is equal to 15 kilometers. Or the distance traveled by the bus plus 15 kilometers is equal to the distance traveled by the car. It's the same. Or you could take the difference of D2 minus D1 and they should be equal to 15. Okay? So the translation of this representation will be d2 minus d1 is equal to 15. Okay? This is now the translation of the representation or the verbal equivalent, right? So if we now try to substitute d1 and d2 in terms of the unknown time, because d1 is in terms of time and d2 is in terms of time, so if we try to put it here, it will be 145t minus 120t equal to 15. Okay? 145 minus 120, they are similar terms. That will be 25t equal to 15. Therefore, t now will be equal to 15 over 25, or t will be equal to 0.60 hour, or this is approximately 36 minutes. Okay, that's it, guys. That's how simple on how to solve problems under distance problems. The only equation that will be needed here is distance is equal to rate times time. And in the formulation of the algebraic equation needed to solve for the unknown, okay, try to take note of the verbal explanation, right? Like in here, after so many hours, the distance traveled by the car and the bus is 15 kilometers. So actually, we could translate this one into an equation, and this will be the required equation. Okay, that's it, guys. So for tonight, those are the example problems for the so-called distance problems, and that will be an application of linear equations. Okay, good evening from Los Angeles, Professor David J. Delosreyes.